Hello. Today we're going to talk about vapor pressure. So again, we're talking about liquids and solids where the particles are condensed or close together. And because of that, the intermolecular forces are significant and they affect all kinds of different properties. So solubility, melting point, boiling point, heat of vaporization, all kinds of different properties. So another property that's affected by intermolecular forces is vapor pressure. And vapor pressure, if you remember, is the pressure that's exerted by the vapor on the surface of a liquid. So let's write that down. The pressure exerted by the vapor on the surface of a liquid. So if you remember, if you have a liquid, no matter what the liquid is, some of the particles here in the liquid are moving fast, some are moving slow, some are kind of in the middle. The ones that are moving fast, if they get to the surface, if they're close to the surface and they're moving fast, they're going to kind of pop out and become gas, right? So those gas particles collide together and collide with the walls of the container, and they cause pressure over the surface of the liquid, and so that is what vapor pressure is. It is the pressure that's exerted, it's the collisions that are happening because of the vapor particles at the surface of a liquid. So we have these vapor pressure curves where we graph vapor pressure versus temperature. And the vapor pressure curves basically help us look at the vapor pressure at different temperatures. And as you can see, as the temperature increases, looks like the vapor pressure is increasing as well. So we indicate vapor pressure at different temperatures. And as your temperature increases, your vapor pressure increases as well. Now, why is that? Well, if you have a higher temperature, that means the average kinetic energy of your liquid particles here are faster, right? The particles are moving faster. And if they're moving faster, then that means more of them can get to the surface and escape and become a gas. And so you have more gas particles at the surface and therefore more collisions or more pressure. So the faster the particles are moving, the more will become vapor and collide and cause pressure. So that's why you see the higher the temperature, the higher the vapor pressure. Another thing that these vapor pressure curves show us is the strength of the intermolecular forces as well. So these curves also indicate the strength of the intermolecular forces. So the stronger the intermolecular forces, the lower the vapor pressure. So why is that? Well, if the particles in the liquid have very strong intermolecular forces, so the particles are very, very attracted to each other, it is harder for them to kind of escape from each other and become a gas. And so if there's strong attractions here, they're going to remain as liquid. Fewer particles would escape and become a gas, and so we'd have less gas particles, less collisions, less vapor pressure. So if you look at the curves again, you can tell, looking at these different substances, so we have diethyl ether, ethyl alcohol, which is known as ethanol, water, and then ethylene glycol. And it looks like the one that has the strongest intermolecular forces is the ethylene glycol. And the one that has the weakest intermolecular forces is the diethyl ether. And the reason is, if you compare at the same temperature, you'll see that the ethylene glycol has the lowest vapor pressure, which means less of the particles are turning into vapor and colliding, and so that means that the particles are really, really attracted to each other. Diethyl ether, on the other hand, has, at the same temperature, the highest vapor pressure, And so that tells us that it's pretty easy for those particles to escape and become a gas, and that means that they're not really attracted to each other as much. Okay, some terms that you need to know about. Volatile. So volatile means easily evaporates. And let's relate volatility to intermolecular forces. So the stronger the intermolecular forces, the more attracted the particles are to each other, the harder it is to separate those particles physically, and the harder it is to vaporize them or evaporate them. And so the stronger the intermolecular forces, the lower the volatility, or the less volatile it is. Boiling point, remember that boiling happens when the external pressure is equal to the vapor pressure. That is acting on your liquid. And the boiling point can change, and so normal boiling point is the temperature at which your vapor pressure is equal to 1 atm. Your external pressure is normal, and so this is the temperature at which the vapor pressure of your liquid is equal to 1 atm. So your vapor pressure curves also indicate boiling points. I guess we could add that on here. Indicate boiling points at different pressures. So basically what we're saying is the liquid will boil when the vapor pressure is equal to the external pressure. And so let's look at diethyl ether, for example. So you can see that these are all boiling points on here because these are all vapor pressures and temperatures, right? And so when, like, let's say the external pressure is 600 millimeters of mercury, that means that diethyl ether is going to boil at, let's say, like 25 Celsius, for example, right? If the vapor pressure, if the external pressure, the pressure in the room is, let's say, 400 millimeters of mercury, then that means that the diethyl ether is going to boil at 17 Celsius or so. So these are all boiling points that were being shown here. So from the vapor pressure curves, you can read what the boiling points are, because again, the boiling point will occur, that temperature that you're going to read is going to be when the vapor pressure is equal to the external pressure. So the normal boiling point is right here, this line, along this line. So the normal boiling point for diethyl ether would be this temperature right here, so maybe like 30-ish or so. The normal boiling point of ethanol is 70 some. The normal boiling point of water is 100 Celsius, and ethylene glycol doesn't really have a normal boiling point. Okay, let's compare the intermolecular forces, the boiling points, and the vapor pressures of the following. So we're kind of putting all of it together here. So sometimes they will give you different substances, and based on your knowledge of the intermolecular forces, you assign what type of intermolecular forces, you assign their strength, and all that stuff. But sometimes they'll give you data to help you figure it out. So you always trust the data, not necessarily what you think it should be. If you look at these are all nonpolar, and so they all have just London dispersion forces. So all LDs. And with London dispersion forces, the more electrons and the bigger the molecule, the stronger those intermolecular forces are. So in terms of intermolecular forces, because they're all LDs, these are going to be the strongest. This is going to be the weakest, and that's kind of in the middle. So weakest intermolecular forces, strongest intermolecular forces. Okay, next is you want to double check that makes sense. So the heat of vaporization, the stronger the intermolecular forces, the higher the heat of vaporization. So check that the data that they give you makes sense, right? So this is the weakest intermolecular force that has the lowest heat of vaporization. This is the strongest intermolecular force that has the highest heat of vaporization. So that makes sense. Your trend is good. You can move on. Let's look at boiling points. And so boiling points go with intermolecular forces. The higher the boiling point, the higher or the stronger the intermolecular forces, right? So this would be the lowest boiling point. This would be the highest boiling point. The ethane will be in the middle. Next is vapor pressure. So with vapor pressure, the stronger the intermolecular forces, the lower the vapor pressure. So this is the strongest of the intermolecular forces, so this is the lowest vapor pressure. And then the weakest intermolecular forces would have the highest vapor pressure. Okay, let's look at the next one here. So we are doing the same thing. We are comparing the intermolecular forces, the boiling points, and the vapor pressure. So let's start with the intermolecular forces first. And so ammonia we know has H bonding. Water also has H bonding. And we know between the H bonding, the water would be stronger, right? But if you didn't know that, they give you data, right? So you can figure it out. And this one just has dipole, right? SO2, I'm going to draw it up here, has resonance. So looks like that. And so even though it has resonance, it's still asymmetric, and so it is going to be polar, and so it has a dipole moment. So what we'd expect is that water has the strongest intermolecular force, followed by ammonia, because it also has hydrogen bonding, and then followed by SO2. But if you look at the data, what we just said is not supported by the data, right? Remember, the stronger the intermolecular forces, the higher the heat of vaporization. If the data contradicts what you think, you go by the data. Because in real life, we study like the generalization, the general rules. There's always exceptions in real life, right? And so if you're given data, that is reflecting the truth. So you go by whatever the data is. So what is the data telling you? Well, the data is telling you that water is the strongest of the intermolecular forces, which is what we predicted. But then it's telling you that this one is number 2 in the middle, and this one is the weakest of the intermolecular forces. Now, does that make sense? Well, maybe. We got to make it make sense, right? We got to explain it somehow. So what is the reason? Well, remember, all these have London dispersion as well. All molecules have London dispersion, right? So in general, hydrogen bonding is stronger than dipole, right? But somehow the sum of these is larger or stronger than the sum of these. Well, what's the reason? SO2 is a huge molecule with so many electrons. its London dispersion is pretty significant. NH3 is pretty small with very few electrons. Its London dispersion is very, very small. And so the London dispersion here is so big that the sum of London dispersion forces and dipole forces for SO2 surpass, are stronger than the sum of the London dispersion and the hydrogen bond. So yes, the H bond here is stronger than the dipole interactions, but the LD here is stronger than the LD here. The sum of these is stronger than these. Now, you wouldn't know that. So if you're not given data, you'd say, oh, NH3 is hydrogen bonding, that's stronger than dipole. But if you are given data, you got to do what the data tells you. So you got to do it that way. So based on the intermolecular forces, then we can do boiling points. So boiling points, the one that has the strongest intermolecular forces, that's going to be the highest. This one's going to be in the middle, and this one is going to be the lowest. When it comes to vapor pressure, it is the opposite trend, because the stronger your intermolecular forces, the lower the vapor pressure is. This one's still in the middle, and the weaker the intermolecular forces, the higher your vapor pressure is. So this box kind of talks about what we just talked about here. So it's telling you this is a very popular question on the AP exam recently. Several molecules are given with varying dipole moments, but the one with the highest dipole moment might not have the highest boiling point. This is because all molecules have London dispersion forces. Larger molecules containing more electrons will have a higher polarizability and therefore stronger London dispersion forces. So it is possible that the London dispersion force is so great that the London dispersion plus the dipole here might surpass the London dispersion plus a stronger dipole there, or a hydrogen.